This paper presents Eulerian video magnification, a method to amplify and visualize temporal variations in videos that are difficult to see with the naked eye. Our method combines spatial and temporal processing to emphasize subtle temporal changes. First, we take a standard video sequence as input and decompose it into different spatial frequency bands using a Laplacian pyramid. We then take the sequence of pixel values over time and apply a temporal bandpass filter to extract the frequency band of interest. The resulting signal is then amplified and added back to the original frames, and the pyramid is collapsed to generate the output video. Our technique can be run in real time, essentially serving as a microscope for temporal variations. The user can specify the temporal frequency band of interest by adjusting the high and low cutoff frequencies for the filter. She can also adjust the amplification factor of the bandpass signal using a slider. Larger amplification results in a larger boost to the temporal bandpass. Changing these parameters can make variations in the scene more apparent, but large amplification can add artifacts to the result, as discussed in the paper. We show how our technique can be used to visualize imperceptible variations in videos, for example, a human pulse. We automatically select and amplify a narrow band of temporal frequencies around the human heart rate, and reveal the variation of redness as blood flows through the face. This approach is robust to different skin tones and small motions. It also allows us to automatically extract vital signs from standard videos. For example, here we extract heart rate measurements of a newborn and confirm their accuracy by comparing them with the readings from the hospital monitor, which was recorded in sync with the video. Interestingly, temporal color amplification can also be used to amplify spatial motion. Consider, for example, this 1D illustration, showing a translated wave at 2 time instants. For a smooth image and small motion, we can filter the signal temporally and get a good approximation to the translated wave. By amplifying the temporal signal, we can approximate a larger translation, essentially producing a motion-amplified sequence. This is analyzed in more detail in the paper. In this synthetic example, the blob has very subtle motions. We filter this sequence temporally using a wide passband filter and boost the temporal signal to generate a video where the motion is much more apparent. Here, several blobs oscillate at different temporal frequencies as shown. By tuning the temporal frequency passband, we can selectively control the temporal frequencies that are amplified. Notice that the same temporal filter is applied to all pixels, and while the spatial motion is amplified, the temporal frequency is maintained. Motion amplification can be useful for medical applications, for example, to visualize artery pulsation. Or for contactless tracking of baby breathing and SIDS detection. Or we can simply make changes in everyday videos more apparent. In this video, we selectively amplify motions of individual strings of the guitar by tuning the temporal filter to the correct frequency of each string. This input video is a blend between 2 still images taken 15 seconds apart. The output video reveals changes in the scene even within this short time period. Finally, in this video we managed to amplify very subtle motions of a DSLR camera caused by its flipping mirror during a photo burst.